Just wait till okay. So henceforth it will be recorded. Okay. So now if we consider a classical path is delta s equal to 0. That means s is not changing. So delta s by h cut, this is 0. So even if this is large number, this can be a small number. Classical limit actually h going to 0, you remember. So your delta s going to 0, h cut is also going to 0 in the classical limit, such that this, if, of course, if this ratio limit delta is going to 0 or delta is actually is 0 and h going to 0 is finite. Delta is actually is 0 and delta h going to 0. So this is the limit. So limit h cut going to 0, this is classical limit. Delta s by h cut can be a small number. It can be a large number, little bit large number, but if they are small number, then this contribution when you go along will add up coherently. How much small, that will quantify. Just wait, little later. But if it is a very small number, then e to the power I theta, e to the power I theta will have a small number, and you can have a, suppose within a pi values, then it can have a all positive sign. So they, in that case, the contribution will add up coherently. This is this adding up contribution coherently for classical path delta s equal to 0 is always true. This is always true because delta is going to 0, so this contribution will be very small. Even if it is 0, then I'll just have a constant integration. I'll have, even if it is 0 e to the power 0, so it is 1, so I'll have a just a contribution, coherent contribution. Now suppose the path is not classical but very close to path. So for example, for C1 path, now for C1 path which is very close to classical path, so what we can assume, that very close to classical path delta s is almost equal to 0. Okay, so if delta s is almost equal to 0, then also if this value is within certain limit, that limit will call is coherent limit. This value is, suppose sometimes we call it's within pi, then this also will coherently add up, and then also it will give some non-zero contribution. Okay, is that clear? So path closer to classical path, and it is coherent in the same sign. It is also coherent that contribution to classical path and contribution to this path will add up coherently. They will have a constructive interference with them, and they can, this path contribution and that path contribution, so they will add up. So path closer to classical path has two roles. First of all, it is also coherently add up when you move along. Not only that, that contribution and classical path contribution will have same sign and they will add up. But what happened to the far away path, C2 and C3? Far away path has delta s is not equal to 0 or not very closer to 0, so it's non-zero. So it will have a random phase. So contribution of C2 also very small or close to 0, and contribution of C3 may or may not be with the same sign with C2. So their adding up contribution also will be less. Okay, so that is why path far away from classical path will almost have a negligible effect. Okay, I think I have stated all the points here. Now think of it and ask if you have any doubt. R. Shankar book has explained chapter 8 this nicely. Now I'll consider one example, concrete example, and we'll try to see. But if you have This argument is very important. Every year, almost every year I ask this question, and student never convey the argument properly in exam. So in exam this year also we may ask this same argument, how you can say that path. So Feynman path integral is that electron or particle can move here to here through any path. All path will have non-zero contribution, but and that all that's add up to give you a quantum mechanics. That we used to calculate that same probability using Schrodinger equation. So that, of course, equivalence is a topic which we'll discuss, but not much details with the equivalence with the Schrodinger quantum mechanics. But we should know what is the path integral. Path integral is now completely, there is nowhere Schrodinger equation will be using. We'll calculate the transition amplitude, and that transition amplitude depends on all possible path connecting the initial point and final point, and they will add up. When Feynman gave this theory, everybody laughed at it. It is impossible that there will be contribution if the particle go from some different path, not classical path. But those contributions, apart from classical path, those contribution gives you the quantum effect. And it is now proved that those effect and calculated from Schrodinger is the same. So that is the whole philosophy of path integral quantum mechanics. Our syllabus, this course is on field theory, path integral field theory. But still we need this concept path integral. So that is why I'm spending time. So we'll not go much derivation. Okay, now I'll consider one example. Suppose I have this a particle at 0, 0 to move at 2, 1, 1. 1, 1. Yeah, 1, 1 is xt. This is initial x is 0, time is 0, final x is 1. So particle can go the classical path, there is no force, so it will be x equal to t, right? Straight line, x equal to t. The point connecting these 2 points will be the straight line passing through these 2 points. So that is the classical path. So this path x equal to t is the path equation, is a straight line. This is your x, this is your t. So xt will be the classical path. Okay, this particle can follow a non-classical path, say parabolic path. So t equal to say x square. This is a parabola equation. So this is, now let us calculate the action for this. So action is the basically integration from 0 time to 1 time, 0 second to 1 second, say, and that half, this is a free particle. I mean, classical path is straight line I have taken, so it is free particle. So v square, half m v square dt. So this is your action. So notice this is a very simple example, but this kind of calculation you may have to do for other problems. So notice it very carefully. So what is your v? So classical path. Suppose I calculate the classical. So classical path v will be x dot. So dx dt should be 1. So it is half m dt. So it is basically half m. Half m is constant. So this. So classical action is half m. Now, if I consider that non-classical path, say that S1 in this case, parabolic path, so it is 0 t, 0 t is 1, half m. Now, v will be dx dt, right? Dx, is that parabola fine, or maybe we can write, okay, so dx dt, yeah, so maybe I think I prefer to write this type of equation, parabola equation. So dx dt will be 2t, 2t, right? So velocity is 2t, so this will be 2t, and then 2t square, remember, 2t square. This you should not do mistake. Velocity is dx dt 2t square and then dt. So we have 4, so 2m, then 0 to 1, t square dt, right? So you will have 2m, this is t to the power 3 by 3, right? And 0 to 1, so basically 2m by 3. So you get a different action. This was the classical action. This is the some action in non-classical path, that parabolic path. So change of action is S1 minus S classical. So this will be 1/6. Difference of this and this will be 1/6 of m. Now let us calculate the value. So now let us call. You all know that action is your arc second, right? Action unit is arc second. Action. So arc second, you know, h is 6.6 into 10 to the power minus 27 arc second. Xn and h has the same unit. I'm writing h, not h cut. So this then you can write 1 arc second. 1 arc second is basically 1 by 6.6 into 10 to the power 27, right, of h. I'm just taking this going this side, so it will be in the denominator. So this is basically approximately 1.6, 1 by 6 into 10 to the power 26 h. Now suppose the particle is a classical particle of mass, say classical particle, mass m equal to say 1 gram. So then delta S will be 1/6, 1 gram, then 1.6 into 10 to the power 26 times h. So delta S by h will be 1.6 by 6 into 10 to the power 26 radian. This much value. So a classical path, this all paths contribution is 0. Even if I look at the classical particle in the quantum path integral formulation, we can see that this value is very less. Now, if you have an electron, suppose an electron, now not a classical particle, but an electron. Now, electron has mass 10 to the power minus 27. So, what will happen? You can have 1/6 into 10 to the power 27. I am not writing the prefactors, but I am just getting an order of magnitude. So 1/6, 1.6, so 1.6 10 to the power 10 to the power 26. So this there is a factor, so it will be order of 1. Is this 10 to the power 26, 27 or less? Radian. Basically, generally, just for estimate, you can take the coherent limit. Coherent limit is pi. So if this value delta S by H is less than pi, we will consider that this is the approximate value. Why pi? That we are assuming that within pi sine cos changes sign. So that is why. So this less than pi, then this is of course no need of mod pi. Then it is within coherent limit. You can find that you want to describe a electron, we need to go to quantum mechanics, because then in that case delta S by h cut is very small and the path around classical path will have significant contribution. Of course, path far away from classical path may not have much contribution, but for electron, classical path and its surrounding path will have contribution. So those surrounding path effects are quantum effects. Okay, so I think this is clear now. Any question on this? This example is also discussed in R. Shankar book. So if you later want to follow, then just read R. Shankar book chapter 8, you will get. But these are all concept should be very clear. You can do similar exercise of your own when I design some problem. Okay. Now next thing is that what is the advantage of path integral? Now here onwards, now one can find, you can consider this path integral for a oscillator, you can consider path integral for a free particle kind of thing, and you calculate your u. For simple harmonic oscillator, you can calculate for particle, free particle, this, all these things, or any other potential which can be solved, those you can. And there are many books, there are books on path integral quantum mechanics, whole book. So those who are interested in this, they can study, but we don't need to go further. Now what I'm going to talk about is something which is what is the advantage and why we are calculating such thing, because basic idea is that we are going to learn quantum field theory. So that now I'm going to consider. So in advantage of path integral quantum mechanics, or path integral formulation rather, quantum mechanics, field theory, everywhere. So advantage, what are the advantage we can get? So main calculation when you do, you are also studying your 401 or anywhere, you need to calculate the correlation function. Correlation function, and that is nothing but also, we, when I discuss the propagator of scalar field, you remember this is also a correlation function. Basically the expectation values have, suppose x at t1 and x and t2, suppose those two position operator, what are their correlation? Is that correlation between point at t1 and point at t2 is basically the expectation value. So suppose I have some final time except and some initial time, so I can take the my notation is the first time and then position. So suppose we are doing in Heisenberg picture. So this is basically your correlation function, 2-point function, 2-point correlation. Correlation function in also statistical mechanics you calculate. Field theory correlation function, 2-point correlation function is basically when I write field operators, you have already seen that scalar field, time order of phi x and phi y, and then expectation value of vacuums. This gives you the propagator. So this is the important that we need to calculate correlation function or 2-point function, 3-point function. 2-point, 3-point means 2-point correlation function, 3-point correlation function, etc. They are also known as the Green's function. So we need to calculate in field theory. Generally, we talk those correlation function as Green's function. In statistical people, they correlation function they use, but they are basically same. We need to consider the expectation value of the product of 3 points, 4 points, 5 points, etc. So first, try to understand what advantage we get in calculating correlation function if in path integral. So that is the topic we want to tell you in next few minutes. So we need to calculate correlation function. Correlation function basically, the if it is 2-point, that is product of those 2 points of position and then its expectation value. And that we know how to calculate in path integral. This is the quantity we know how to calculate in path integral. So let us first calculate this quantity with our knowledge of path integral. So let me write clearly. So TF XF and this is time order. Suppose I assume T1 greater than T2. Suppose Heisenberg position operator at T1 time, Heisenberg position operator. Heisenberg means Heisenberg picture we are using. So T initial, X initial, and these are Heisenberg states. and we are assuming these are time ordered. T1 greater than T2. So what I can do, I can write this because I don't know how to calculate, because this is not a eigenstate of T2, right? It is a eigenstate of a Heisenberg position operator at T initial, but it is, so I cannot calculate. Similarly, this I cannot calculate because this is not eigenstate of that. So what we'll do, we'll use the completeness relation. Remember the completeness relation, T1 x1 t1 x1 integration x1 is unit. This is the completeness relation. So I'll insert those completeness relation in such a way that these operators acts on eigenstate. So let us do that. So first let us do x1, because there is a operator in t1 and another will x2. So two completeness relation will insert carefully such that they can directly act on those operators. Okay. So this then you tf xf then xh t1. So this operator should act on t1 x1. So I put a completeness relation t1 x1 here. So this times this is unity. Then xh t2, and I'll put t2 x2 here, and then right here t2 x2, and then t1 initial x initial. Okay. Now look at that. This is the eigenstate of this. This is also eigenstate of this. So I can replace their eigenvalues. When a operator acts on the eigenstate, it gives you some number times same state. So this will give you this integration dx1 dx2, and then x. Now I am writing small x, not capital X. X of t1, and from here x of t2 will come out, and then this t initial, t final, t1 x1, then t1 x1, t2 x2, and then third will be t1 x1, t initial, x initial. Okay. So now this operator acts on this state, give these eigenvalues. Eigenvalues are the not operators, they can come out of these things, and we can. So this idea of inserting completeness relation is important, that you have to be master on that where to insert, how to insert, when to insert this, and almost this is the technique is needed, expected from your learning. Now these are harmless quantities, or I am sorry, this should be written as x1 and x2. Yeah, because those are like that. Okay. But this quantity we already know. This is the quantity which is path integral, right? That yesterday last class derivation, remember, this is nothing but path integral with this. So basically what we have, dx, then x1 t1, x2 t2 e to the power I h cut s. So this is our correlation function. So in path integral formulation, correlation function is this. And now these are numbers. These are not operators. So I can have any order. I can write x2 first, x1 first. I can write, they are commuting numbers, C numbers. So that is the advantage. When we calculate the correlation function by this formula, or in our canonical quantization field theory, we need to follow the time ordering. But here in this final formula, we don't have any time ordering. So time ordering you can eliminate in path integral formulation. Okay. So now this we can generalize this thing. Suppose I need to find the expectation value of some operators, say O1, which is function of x at t1, kind of thing, O, say capital N, function of x at capital Tn, kind of operator between t initial and t final states. So this will be simply dx. I'll take these operators, will be substituted the eigenvalues of the position operators, So this O1, now this is operators. This is operators. O is operator, which is the function of this exposition operator. O is operator, and they are now replaced by the eigenvalues. X1, X1 may be right. X1 means X1 at T1. So O1, O2, X2 kind of thing, and e to the power I by H cut S. So in path integral formulation, we just put that, consider those operators, put their, those are function of some operators, so put those eigenvalues there, and this will be a number, and that you put inside the path integral. So you get that expectation value of those numbers. But this is the this formula, and particularly this formula will be using rigorously in our field theoretic description, which in next week we'll consider. We'll start the field theoretic calculation with this path integral formulation. Okay. So remember, when we discuss the one mathematical trick, we have 10 minutes, we will tell you, and then we'll stop. So one mathematical technique which will be useful for our later study is that uh, mm, is that when we calculate the propagator in quantum field theory, uh, we need to calculate propagator, and we know the propagator for scalar field theory. If you remember, I derive it is, say, phi of x and phi of y, and time order, x is 4 vector, y is 4 vector. So this times this is your vacuum at t equal to plus infinity. This is a vacuum at t equal to minus infinity. That means vacuum means the ground state. I am saying the particle, the system was in the ground state in the long past. My infinity we cannot understand, zero also we cannot understand, but infinity, zero means very small number, infinity means very large number. So long past system was in the ground state. Long future means after long time system again will be in equilibrium. So if those are the two ground state, two vacuum in field theory language, then this was our propagator, scalar field propagator. So this we can calculate in path integral formulation. So let us not going to do in terms of field, but suppose my initial time and final time are long and infinity. So TF XF still I am using, and suppose I want XH T1 and XH T2, these two time different time, and they are ordered. So T1 is greater than T2. Suppose we want to calculate xi ti. This is the quantity we already calculate, but we want to calculate this in terms of little bit some mathematical trick to calculate this quantity. You know this quantity, right? Okay. So this quantity is this quantity. Let me write d of x, x1 t1, x2 t2, or maybe x at t1 and x at t2. That so notation is little bit confusing, so no need to write x1 and x2. Meaning is that when my understanding, when it was t1 then it is x1, when it is t2 is x2, and e to the power I by h cut s. This is the quantity, and I am going to tell you a mathematical trick such that I can calculate this quantity. Okay, so let me start with this quantity, x e to the power I h cut s, and I use dt of j t x t. This I add. So this you can think of that limit j going to 0 this quantity dx e to the power IH cut j going to 0. Limit j going to 0, this quantity. We will take the limit at the end. But now suppose I differentiate this quantity of j of t1 I by h cut. I by h cut is there. So what I'll get? I'll get ds, and when I differentiate the exponential, I'll get IH cut, and jt is differentiating with respect to, so I'll get a x of t1. There will be a delta function. Delta function will remove this integration. So delta function will be delta t of t1 because jt is differentiating with the j of t1. So functional differentiation. So you'll get a delta function will remove. So I'll get this e to the power IH cut s plus IH cut the jx term, right? But now if I multiply this with minus IH cut and then del del of j x1 of this quantity. I'm not writing all details, but you can understand why I multiply this factor to cancel this factor. Minus I with plus I will be 1, h cut in the denominator, h cut in the numerator, so there will be 1. So basically you will get dx and then x of t1 e to the power I h cut s, because I'm not writing j here again because you have to take the limit j going to 0. So if I need to bring a operator like xt1, I'll differentiate this quantity introducing a j source term. Mathematically it is called source term, and then I take this kind of operation. And if I take this kind of operation 2 times, del 2 del j of x1 delta g of x2 on this dx e to the power IH cut s plus IH cut dt of j t xt, then basically and then taking limit j going to 0 outside. First I will differentiate, then we'll take the limit. So basically we'll get this dx x of t1 x of t2 e to the power IH cut s. So to bring these two down from the exponential, I use this mathematical trick. Nowhere, j is nowhere present. It was there initial, we introduce, we take the limit, but in between we do this differentiation such that we can get. Is that trick clear? So when we need to find the expectation value, which actually the calculation of propagator, x of t1 x of t2 times initial time final time. So this is basically this quantity, and that we can calculate through the operation. So this quantity I can write minus I h cut whole square d of j1, j1 means j of t1, d of j of t2 times ds d ds e to the power IH cut s IH cut integration dt jt xt. Okay, so this mathematical trick is clear to you. So I will not, we don't have to do this this integration very will without but this quantity is basically, this quantity we know how to calculate. This is the path integral in presence of g, but this we know. So if we can calculate that, we take the differentiation 2 times with respect to this parameter j we introduce, and we get this. Okay, so maybe I'll stop here. If you have questions, please tell me your question, or if you need to explain something, I can explain. So this now next topic is remaining the equivalence. I'll make some comments about the even in 5 minutes I can cover that equivalence also, but equivalence derivation will not do. Equivalence of path integral formulation, equivalence of Schrodinger and path integral quantum mechanics, this I'll just statement I'll give you. Proof is given in Arshankar. This is a simple quantum mechanics book accessible to all MSc student. Proof is given in Ashok Das, and so this equivalence I suggest you to study from Arshankar or Ashok Das. Just you study yourself. If you have some steps problem, mathematically it is basically Taylor expansion and the kind of no rigorous mathematics is needed. So this topic I will not teach. Next week, Tuesday class, we'll start with the field theory. Maybe in the tutorial, 2 tutorial classes I'll take. So if you want to use this tutorial class as your preparation for your NET exam, which is 29th, is welcome. So I can discuss some problems in quantum mechanics, statistical mechanics, mathematical, classical, etc. So, but only to these students, this our elective paper students, and please, if you have some doubt of particular type of question, please let me know beforehand in these subjects, that I can give you idea how to calculate those. So please, you are taking preparation of your NET exam, and you may have stuck with certain kind of problems. So list down those problems, send it to me beforehand. This is Thursday class. By tomorrow you send it, and then if I may not able to answer all your queries, but I'll try to give, and I'll give you some tricks and some type of problems how to deal with this kind of things in this 2 tutorial class. And apart from, of course, if you have some queries, question, whatever taught in last 5 lectures, as I promised that every 5 lectures there will be tutorial class, so that, so I purposefully take this to next 2 classes on tutorial class. Okay, any question? But do send your problems or difficulties, in particularly in these papers, statistical, quantum, classical, these 3 mechanics, and some mathematical. So I'll answer your queries tutorial class in this, because you have not given any problem set. Now next week we'll give you problem set on this part, 5 lectures, and then we'll have next tutorial class, we'll discuss those problem sets or kind of thing. Okay, so let me stop here.